The next section of this talk is really focusing in on matching the water treatment system to your goals. So we talked about physical water quality. The most important aspect of that is total suspended solids. The thresholds in many of these parameters is not really all that exact, but the recommended level is to have less than 100 parts per million or milligrams per liter, same thing, of suspended solids, or there will be a very severe case of clogging of emitters. The treatment to remove suspended solids is through filtration. Here's a couple of examples of greenhouse filters, but there are many filter types. On the left we see a media filter, and on the right a vibrating screen filter. Total suspended solids is a number that you can get when you send a water sample into a laboratory. What they'll do is they'll filter it out and weigh how many milligrams of solids are collected on a filter through 1 liter of water. So here, for example, we were filtering before and after this media filter, paper screen filter, in a greenhouse in Michigan. Before the filter we had 12 milligrams per liter. Afterwards we had about 6, so we had a 50% reduction. So the suspended solids is a useful number if you want to check whether your filtration is working. There are many aspects of the chemical quality of water. Here are a few of them. Alkalinity is essentially dissolved limestone. Hardness is calcium, magnesium. For both of those situations, typically we want less than about 300 parts per million or milligrams per liter. The treatments may be acidification to drop the pH and neutralize the lime. Could be from a fertilizer point of view using an ammonium-based fertilizer, which has an acid reaction in the soil to balance the alkalinity. And also sometimes growers will use a reverse osmosis system or rainwater and blend in with typically their alkaline well water. In terms of pH, we already mentioned that pH is mostly important in terms of solubility and activity of certain chemicals, such as fluorel requires a low pH. And the treatment is typically acidification. High salts, such as a coastal nursery dealing with saltwater intrusion, we have thresholds of EC level of less than 2 or less than 1 if you're growing plugs and propagation, and sodium chloride being less than 70 parts per million. Here what we're trying to do is to blend in with rainwater, reverse osmosis water, or we're having to leach out on a management point of view to avoid salt buildup of these junk ions in the growing medium. There are many other specific problems. Boron, iron, manganese, all of them have particular management approaches to deal with them. For example, growers here in Florida with high iron will often take their well water, put it into a settling pond, oxygenate it to form rust and have that iron settle out. They'll filter and then use that water for irrigation. So let's take an example of these 3 water types here, sample A, B, and C, and some different numbers here, pH, alkalinity, EC, and sodium. And let's think about challenges for each of those waters. Sample A is the sample that would give you the highest media pH. Even though it doesn't have the highest water pH, that high alkalinity level means that it's got a lot of dissolved limestone. So that grower is going to have to probably acidify their water source to stop media pH climbing too high. Sample B has got a high pH but a low alkalinity. Also has a low EC. Up in New Hampshire, where I used to live, we often had water like this. Even though the pH was high, it's not buffered because there isn't much lime in the water. And in fact, the media pH is not very much affected by this water source. In sample C, we have a situation with a water source that has a high level of sodium in it and a fairly high starting EC before we've added any fertilizer in. That grower is probably going to need to leach out on a regular basis to stop salt buildup in their containers. And then the final category of water problems are biological ones. So it could be pathogens, and there are presence-absence tests available. There are some quantitative tests, but those are very much in development. There are bacteria. I'll show you a test type for quantifying bacteria levels. And there's also a practical way of seeing biofilm and algae problems in terms of whether that's actually leading to management problems. In all of these cases, the treatments are going to be some type of filter and some type of sanitizing chemical. I mentioned a method for quantifying bacteria. And traditionally, on the left, you're seeing an agar plate. Now, on the right, what we're looking at is we're looking at a Petrifilm. It looks like a little sticky card. So rather than having the sterile conditions, lab conditions for an agar type culture, we have a method that is being modified for grower use here at the University of Florida, where we have a kit that you can take a sterile sample in a sterile container. You can plate that out onto one of these sticky card type Petri films, put it into a drawer for several days, and there are sticky cards, Petri films for aerobic bacteria or for yeast and molds. Now, these numbers here, these dots that represent these colony-forming units, they don't necessarily represent pathogens. This is a non-specific test. But what it will do is it'll tell you how much biological load is there in that part of your irrigation system. And we found this to be useful to see, for example, before and after the application of sanitizing chemical, is there a drop in the colony-forming units per milliliter? It's an easy-to-use method. We know it works well on site, and through the University of Florida you can get more information in our Water Education Alliance for Horticulture website. It's a non-specific test. It's a measure of microbial load and biofilm risk. For specific pathogens, a water sample can be sent off to a lab, and there's two basic approaches. One of them is that they will plate out on a selective medium, typically to the genus level, but sometimes to more specific level. For example, at the University of Massachusetts, for $50, they will plate out a water sample and identify presence or absence of Fusarium, Pythium, Phytophthora, or Rhizoctonia. At the University of Guelph, they'll essentially take the DNA fingerprint of a water source, and they will see whether there is a match between the DNA that's found in your water sample with about 79 pathogens. Now, I mentioned that the goal here is to match your choice of water treatment with the goals that you're trying to achieve. So here's a couple of specific ones. One of them is biofilm removal and suppression. So you've got an irrigation system where you're getting clogging of emitters and you're not able to control the microbial growth in your lines. The first thing in any type of sanitation is to remove material by cleaning before sanitizing. So flushing the system, power washing any surfaces that are exposed is important. The next is to shock the system with a high concentration of chlorine dioxide, activated peroxygen, the most common chemicals. Some people will do this with chlorine. And that will stay in the lines overnight, and then it'll slough off some of the layers of biofilm, which will then be flushed out of the lines. An important aspect of the shock approach is that the concentration of active ingredient is way too high for that water to come in contact with your crop. So you need to somehow have an ability to flush these lines out, doing it into an empty greenhouse or field, and doing it between seasons if possible. When it comes to suppressing buildup in new irrigation lines or cleaned out lines, then many of the sanitizing agents will work. They're adequate for suppression of biofilm buildup, but not all of them are as effective in terms of removing an established biofilm. For algae and pathogen control, there are point treatments, for example, heat or UV, but there are also residual treatments that will carry an active ingredient through the irrigation system. This is called residual activity. And the goal that we have here is to kill the spores, both from the water source, for example, it could be a pond, from the biofilm in the irrigation lines, and potentially to have some algae suppression when if there is any residual active ingredient as the water comes out the emitters. So examples of chemicals with residual activity are chlorine, copper ionization, chlorine dioxide, activated peroxygen.